So let me, okay. So, okay. So is it visible there? ይታያችኋል? ሄሎ ይታያችኋል ወይ? የሚታይ ከሆነ እጃችሁን አንሱ እስቲ። እያየው ነው። እጅን አንሳ በቃ። ፒፒቲ ይታያችኋል? እኔ እያዩችሁ ስለሆነ ነው። እጅ አንሳ። ማን? ኤፍሬም። ኦኬ ይታያችኋል? ግሬት። እሺ So we represent each of these aerodynamic coefficients in terms of the dimensionless quantity. And these are the four forces acting in the straight level flight. And another important thing is the stall velocity, which is corresponding to the CL max condition. So in the region here, the CL versus alpha graph is linear, but at some point it will start to deflect, so that the maximum point is the stall point. So that is represented with CL max. So V stall is a function of CL max. On that, we tried to see this example. We already solved this example, so I can go directly to the plan form area of that the previous discussion. Okay, so this is the plan form area and the chord lengths. Actually, these are the dimensions of wing. So in the actual wing, you can see the chord as well as the area, the plan form area. So the plan form area is in meter square. That is useful for the calculation of lift as well as drag and moment. And the chord is the dimension from leading edge to trailing edge of the wing. So, and the distance from one tip of wing to another tip, we call it as the span of the wing. So that are representative part. Anyways, so different geometries may have different cross-sectional area as well as the lengths. For example, for the circular object or for cylindrical body, you might have diameter as length, and the total area is pi d square over 4 is the area representation. Okay. So now let's take some part of the wing, which is representative part of 3D wing. So in 3D wing, you can observe the aerofoil itself, which represents the chord and the thickness of the wing, as well as the length of the wing also. That the wing length from one tip to another we call it as B. So this is the portion, okay? So once we take this, we can resolve the, just take the differential length ds from the wing or the aerofoil. So for this ds can be resolved into dx and dy with some angle theta, because it is curved profile. So that dx is ds cos theta, dy is minus ds sin theta, because dy is in the downward direction and dx in the right, towards to right, so it is positive, and s is a function of the chord length. Okay, so this ds is a function of chord length. Okay, we can represent in this direction. Okay, so that is the total surface. So how we can represent that ds here? Okay, it is, I think, letters. Yeah. እዚህ ላይ አልተገለጸም እንጂ ዲስ ሳምዌር ሪፕሬዘንት ለማድረግ ሞክረናል። ሶ ከኮርድ ሌንግዝ ጋር ነው እንትኑ። Okay, so this is the geometrical relationship between different lengths of the wing. And using these equations, we can develop the CN, CA, and CML. So this CN, CA, and CML are representation for the normal force, axial force, and leading edge moment in the aerofoil case. Okay, here the small letter represents for aerofoil, but previously we developed these equations for the three-dimensional wing already. That we can go back and we can see. So this relation gives us finally the lift coefficient CL for the aerofoil is Cn cos alpha minus Ca sin alpha, and CD, or the drag coefficient for the aerofoil or the infinite wing, is Cn sin alpha plus Ca cos alpha. So these relations are directly taken from the aerofoil. Hello? አቤት።
ተቋርጦ ነበረ፣ አላየንም። ኢንተርኔት ተቋርጦ ነበር።
ኦኬ ኦኬ፣ እሺ። አሁን ተመልሷል?
አሁን ነው የተመለሰው።
ስለዚህ እንደገና ሼር ላድርገው ወይስ ሼሩ ይታያቸዋል?
ሼሩ ይታይናል ግን አላየንም ነበር እስካሁን።
ኦኬ፣ ስለዚህ ችግር የለም። ሪቪዥን ላይ ነበርኩና we can see it again. እሺ። Okay, so let me start from again the planform area and actually the dimensional relationship. So this is the wing, three-dimensional wing, and the three-dimensional wing is characterized by thickness, the chord length, and the span of the wing. So the span of the wing is from the tip of the wing to another tip of the wing is called span. We have leading edge of the aerofoil and trailing edge of the not aerofoil but the wing. So the distance from leading edge to trailing edge is called the chord length. So that the chord length is variable, because if you take the cross-sectional cut from this point, the chord length is some C. But when you go to tip, because this is a kind of tapered wing, so that you can get less chord. So it depends. Therefore, we consider the mean chord. Okay. For the overall analysis, we use mean chord length. And the area of this wing is given with S, that is in meter square, and the chord is in meter. So the flow direction of the aircraft is in this direction, and the stream velocity indicates the opposite direction of the flow. Okay, so now for different shape, we can find different area or cross-sectional area dimension. For example, for circular object, pi d square over 4 is the dimension or the area, and the length of or the chord is equal to the diameter, that is d. And if we take this aircraft wing, this aircraft wing is three-dimensional because it has thickness here and chord here, chord length, and also length L. So L times T times C will give us the volume of it. So it is finite wing. This is called finite wing, and the geometry of the finite wing. If we take a small differential length ds from the wing, exactly at this point, then what we can resolve it into x and y. So the differential length dx and the differential length dy are represented by dx and dy, and the angle of inclination of at any small distance or differential distance d theta is there. So dx is equal to ds cos theta and dy is equal to minus ds sin theta are the relation. And the overall planform area of this wing is given with C as a function of length L. Okay, C, the chord, because this is the chord length, and the area is the function of ds. So if I extend this point, the point, project this point to back to this point, then we can find some differential area. Okay, that differential area, the sum of that differential area gives us the total surface, or what you call planform area. And then the aerodynamic coefficients for the aerofoil, which are represented with a small letter here. But previously, we already captured these formulas for the three-dimensional case in the capital letter. So Cn is the normal coefficient, Ca is the axial force coefficient, and Cm is the pitching moment coefficient about leading edge. So these formulas cumulatively given here. So this Cm is with Cn and the Ca combination. So it is a kind of long formula. So finally, after some rearrangement, what we can get is Cl and Cd directly from Cl is equal to Cn cos alpha and Ca sin alpha with minus sign. And the Cd is Cn sin alpha plus Ca cos alpha, as we have done before here. I can go back to the N and A force. Normal and axial forces are given here. Moments are developed for each the upper and the lower surface. So in this case, what we are developing is for the three-dimensional wing case. But the recent case is directly for the two-dimensional aerofoil case. So the moment also given here. Okay, so these things are taken. As I said, the chord is a function of, so this is what ds is differential length from this point to this point. We took ds. That's why this picture is directly equivalent with the previous this picture. Let me bring you that picture and this one. Yeah, so you can extend this point to here and this point to here and shade it. May I shade it? Actually, yeah, I can. Okay, not pointer with. Okay, let me write it like this. You can extend it like this. And this is our ds. No, yeah, it is ds actually. Okay, so once we get CL and the CD, that are our important coefficients. So we can directly calculate the lift and drag of aerofoil. So the lift of and drag of aerofoil are not directly equal to the lift of and drag of three-dimensional wing. So in the book named Aircraft Performance and the Design book, which is written by John D. Anderson, you can find what are the relation between the three-dimensional and the two-dimensional wing. Okay, so they have a small difference, but for our convenience, we use the same formula for both. Now, once we understand this, let's see the example on that. Consider the supersonic flow over 5% half angle wedge. This is half angle wedge is here. Yeah, you can see here, this is a wedge. And as I told you in the supersonic flow, there is an attached kind of shock wave happen here. So this is the shock wave on the supersonic flow, but this is the wedge, or the body of the wedge is here. Half angle is 5 degrees here. Okay. Then the free stream Mach number ahead of the wedge is 2. So the free stream Mach number means what? It is the ratio of flight speed divided by sound speed. That means the free stream Mach number 2 indicates that the flight velocity is 2 times of the speed of sound. And the free stream pressure and the density are given 101 times 10 raised to 5 Newton per meter square. And the density is 1.23 kilogram per meter cube. So let me show you. So the pressure at the top and the pressure at the bottom are given here, which are Actually, this is 100 and yeah, the free stream pressure. Free stream pressure 1 times 10 raised to 5 Newton per meter. As you know, it is 3 to 5 in actual case, but here we simply use it as 101 times 10 raised to, that is free stream pressure. Again, free stream density of the air density 1.23 kilogram per meter cube. You see, this is the pressure, and the Mach is 2. These are given. The pressure on the upper and the lower surface of the wedge are constant with distance s and equal to the other. So Pu is equal to Pl, which is equal to 1.31 times 10 raised to 5 Newton per meter square. So you can observe from this picture. This is the pressure distribution. Constant pressure is acting over the wedge. This is the wedge. On that, constant pressure of 1.31 times 10 raised to 5 Newton per meter square is acting on the surface. Okay, fine. At the same, the shear force also given. The shear force on the wedge is tau is equals to 431. It is a function of time, that is s to the power of minus 0.2 is given. Okay, and the chord length c is equals to 2 meter is given here. Okay, so this is the shear stress distribution and the pressure distribution, because almost all aerodynamic forces are the part of shear force and the pressure distribution and shear force distribution. So the pressure exerted on base of the wedge is equal to actually in this direction. In this direction, the pressure is equal to the ambient pressure. Okay, that is the meaning. So as seen from this picture, the shear stress varies over both the upper and lower surface as 431 times s to the power of 0.2. And the chord length C of the wedge is 2 meters. So calculate the drag coefficient for the wedge. What is required is drag coefficient. Now, these are the given informations, and based on the given information, we are going to calculate the drag coefficient. So how we can calculate the drag coefficient? That is the question. So we have this equation, drag is equals to integral from leading edge to the trailing edge for the upper Pu, pressure at the upper surface sine theta plus, theta is already given, 5 degree. Pressure at the lower surface is given, shear stress at the upper surface given. So we integrate it in terms of ds, SU. Again here for DSL, we have pressure at lower surface, shear force at lower surface. So we can use this formula. Okay. So now these are the relations actually. These are Pu sine theta, DSU means you can substitute all the values of this thing. And then what we can get is about 5,260 Newton forces obtained from this formula. Again, for the lower surface, we calculate the same thing here using this relation actually. We have these relations. So applying that, finally what we can get is, similarly as the lower surface also it is same, because pressure distribution are the same, the wedge angle are the same, 5 degree. So 5260 Newton is the force. So the total force is the sum of the two. This gives us what you call pressure drag component. And the shear force, the one which is related with the shear force from using this diagram. Hello? So using this diagram, what you can get is the shear force at the upper surface is 936.5 Newton, the lower surface 936.5, and then finally we can sum up all the drag forces. So due to the pressure, it is pressure drag, and due to the shear force, it is called skin friction drag. So we have the summation of pressure drag plus skin friction drag. Overall, some of them gives us about 1.24 times 10 raised to 4 Newton force of drag. Okay, so once we get the drag, we have a drag coefficient relation. So the drag coefficient relation says d over the drag d over q. Q is the dynamic pressure times the surface or the area. So in order to calculate CD, we have to calculate first the dynamic pressure. And to get dynamic pressure, we have to calculate the free stream air velocity. So the velocity of the free stream is twice sonic speed, so that the sonic speed is of sound speed. Sonic speed means sound speed. So sound speed is equal to gamma RT. So temperature of the room temperature is considered, which is 288. And the gas constant R is 287 joule per kilogram Kelvin. And the specific heat coefficient is 1.4 for gas, which we are operating, it is in the gas. So that just substitute it, then you can get 340.2 meter per second. So this is only in the 15 degrees centigrade ambient temperature condition. So if the temperature condition changes, this value will change because it is dependent on the free stream temperature. Okay, so now once we get the sound speed, then we can calculate the velocity of free stream. So the velocity of free stream is 2 times of the sonic speed, so that you can multiply it by 2, so we can get 680.4 meter per second. And then you can apply this thing. Q, the dynamic pressure Q is equals to half rho V square. And then finally you can get the dynamic pressure of 2.847 times 10 raised to 5 Newton per meter square. Okay, so for the given wedge, S is equal to C times L. So we have given that the wedge length is 2 meters. Okay, and we have L is considered a unit length. Okay, considering a unit length, it gives us 2 meters square is the total planform area. Okay, then CD is equals to directly apply. Okay, so S is given, Q is given, D is already calculated, then you can find the drag coefficient, which is 0.022. That is drag coefficient of ከኔ ጋር ናችሁ? Just raising by your hand. Yeah, okay. ገብቷችኋል አሁን ሶልቭ የተደረገው? ከየት መጣን? ድራግ መጀመሪያ ፈለግን። ከየት ነው ድራግ የተፈለገው? የተለያዩ የድራግ ኮምፖነንቶቹን የስኪን ፍሪክሽን ድራግ እና ፕሬሸር ድራግን ኮምፒውት አደረግን። ዘን አፍተር ሁለቱን ሳማፕ ስናደርግ ድራግ አገኘን። ድራግ ካገኘን በኋላ የድራግ ኮኤፊሽንት ለማግኘት ድራግ ዲቫይድድ ባይ ዳይናሚክ ፕሬሸር ታይምስ ኤሪያ። ሶ ዳይናሚክ ፕሬሸርን ማግኘት አለብን። ዳይናሚክ ፕሬሸር ለማግኘት ደግሞ ቬሎሲቲ ያስፈልጋል። ሶ ቬሎሲቲ ካልኩሌት አደረግን። ከምን? ከሶኒክ ስፒድ ሪሌሽን ማክ ነምበር ተሰጥቶናል። ዘን ሶኒክ ስፒድ መፈለግ ነው። ዳት ኢዝ ሳውንድ ስፒድ። ከሳውንድ ስፒድ ካገኘን በኋላ ቬሎሲቲ ያገኘን። ዘን ቬሎሲቲ ካገኘን በኋላ ዳይናሚክ ፕሬሸር አገኘን። ኤሪያ ወይም ፕላትፎርም ኤሪያ የምንለው ሲ ታይምስ ኤል ኦር ሲ ታይምስ ዋን ኢዝ ዩኒት ኤሪያ ፎር ደ two-dimensional object, because this wedge is two-dimensional. we cannot represent it by 3 dimensions. So just taking a unit length, c times 1 gives us 2 meters. C is 2, 1 is 1, so that's 2 meters squared. Then you can directly apply it to this equation, and then finally you can get the drag coefficient. Another similar kind of question also there. It is there on the book. So I address you to refer the John Anderson book of aerodynamics in order to solve this problem. So it is already there on the book. So let me give you a chance to see it from the book. The solution also here for your further discussion, you can see this solution. Okay, then let me come to the center of pressure. So as I discussed earlier, the center of pressure is the point. It is just a point on the, it is a location where the resultant of distributed load effectively acts on the body. So that is the point where resultant force acts. We have seen that what the resultant force is before. So maybe the resultant force acts in this direction. Okay, and when we resolve this resultant force, we can get the axial component of force here, that is the drag component, and the normal component of the force, which is the lift component here. So, so that is the meaning of center of pressure. Okay, so the normal N and the axial force A on the body are due to distributed loads imposed by the pressure. Normal is because of the pressure, and the axial is because of the shear stress. Okay, so all the axial components are due to the presence of shear stress distribution. And the normal force are due to the presence of the pressure distribution. So just taking this picture, this is your leading edge, and you can represent some arbitrary point here O. So we dimension it from leading edge to point O. So that is XCP. XCP is center of pressure. And put the normal force and axial force on that. Then you can equate it with the leading edge moment. The moment at leading edge is given here. So moment about leading edge is equals to, so the representation of moment when it pitches the nose up, it is called positive moment. And when the force creates a nose down moment, then it's called negative moment. So the first one is nose pitching up moment. But the force, normal force creates what kind of moment? Nose pitching down. Therefore, moment about leading edge is equals to minus of XCP times normal force. So the normal force creates negative moment, and the leading edge moment creates positive moment because it is like this. Therefore, from this, we directly find the XCP, the location of center of pressure from the leading edge of the aircraft, right? So that is XCP is equal to minus of MLE divided by N. So that is called the center of pressure. So if the normal force, if sine alpha, that is the angle of attack is very small, then sine alpha is 0 and cos alpha is 1. Then the lift L is equal to the normal force, and the drag D is equals to the axial load. Therefore, XCP becomes moment about leading edge divided by the lift force. So that is directly from the previous equation. So in this case, if you see it as normal force N or lift L decrease, XCP increase. That means the distance from the center of pressure shifts backward. This is about the stability and control condition of the aircraft. If the lift force is small, means lift force is small means XCP is large. If lift force is high and higher, then what happens? The XCP is smaller because they are inversely proportional. XCP and the lift are inversely proportional. Okay. As the force approaches to zero, the center of pressure moves to infinity backward. That means unstable condition may happen, right? So now let's illustrate this condition in much broader sense. Okay, so in this picture you can see three different pictures. One is the one where the pitching moment is extremely at the leading edge. When it is extremely at the leading edge, then the second one is moment is acting at some point. We don't know that. The quarter chord point. Look, C over 4 means quarter chord point. And the moment about quarter chord point is there, and the lift also is there only. So here, lift also leading edge, moment is in the leading edge. Here, lift as well as the moment are at the quarter chord point. So moment about leading edge is equals to moment about, the C over 4 times L. C over 4 is the distance. L is force, so distance times force. And this lift force produces a negative moment because it creates a pitch down moment to the nose. And the moment about the quarter chord is here. This one is positive, right? Then the third picture tells us that the resultant force L and the D are acting at some arbitrary XCP point. Look, this is XCP point. So minus of XCP times L gives this thing, our mid moment about L. So we have three relations, relation 1, relation 2, relation 3. So we can relate this one with this one. That means moment about leading edge is equals to minus XCP times L, or moment about leading edge is equals to minus of C over 4 L plus moment about C over 4. Moment about C over 4. That means moment about quarter chord. Again, we can equate this one. So from this only you can find more than about three equations, right? You can create three equations from here. So this is about the center of. So in the left figure is this one. The resultant is placed at the leading edge with finite value of moment about leading edge. In the middle figure, the resultant is placed as a quarter chord point with finite value of MC over 4. And in the figure in the right side, or the last figure here, the third one, the resultant is placed at the center of the pressure with a zero moment about the that point. When the resultant force is acting through the center of pressure, there is no moment about leading edge, that it balances the force. Okay, so the force alone can balance the aircraft. So that is the meaning. So let's take one example on that. This is example number 1.3. Low speed incompressible flow. The following experimental data are observed for a NACA 4412 aerofoil section at angle of 4 degree and angle of attack 4 degree. CL is given. That is CL. This CL is for the aerofoil. Don't forget, it is not for the three-dimensional wing. CM over C over 4. the moment coefficient about quarter chord is equal to minus of 0.09, then calculates the location of center of pressure. So these are the given parameters, and they require this XCP bar. XCP bar means XCP divided by C. That's called XCP bar. So what we are calculating is XCP bar. So how we can solve? From the previous, equation number 122, directly applied. Minus of XCP L is equals to minus of C over 4L plus MC M of leading edge about C over 4. Just taking this, we can calculate. So let's divide both sides by left L. Then we have left C times L prime, L over L minus MC, because the minus sign also comes here, it creates this one plus and this one minus. So finally, what we can get, C over 4 minus moment about quarter chord divided by lift. So let's substitute. Now divide both sides by C. Actually, moment about quarter chord is given. Moment about quarter chord is half rho v square SC. C is chord, and C